In this section, we will want to write the 3x3 versions of the matrices for the symmetry operations of the molecules that we're interested in. So the first matrix in a 3x3 version that's easy to write is the identity matrix, the E, also sometimes known as C1. Remember that we had seen in 2 dimensions, that is 1, 0, 0, 1. We notice that we have 1s along the diagonal and 0s every place else. So that's what it looks like in 2 dimensions. We can extend it easily to 3 dimensions by continuing the 1 along the diagonal, and all the other positions are going to be 0s. So we say that the E matrix is a diagonal matrix because all the entries that are not 0 are along the diagonal. So this is the 3x3 version of the identity matrix. We can verify this is true pretty quickly. Here we end up using X, Y, and Z, so we have a triplet, an ordered triplet, to represent a point as a column matrix. And if we do the multiplication, it works the same way as in 2 dimensions, in that we multiply the first row times the first column. So I have 1 times X plus 0 times Y plus 0 times Z, and that gives me X for the first position, first column, first row. The second row is 0, 1, 0, and we multiply that times X, Y, Z, so we have 0 times X plus 1 times Y plus 0 times Z, which gives us Y. Last but not least, the third row is 0, 0, 1. When I multiply 0 times X, 0 times Y, plus 1 times Z, I get Z. So we see that we transform the point X, Y, Z to the point X, Y, Z, and it does exactly what we imagined for the identity to do. So we demonstrated this actually acts as the identity matrix, equivalent to a C1 operation. Similarly, we can write and easily extend the inversion matrix from 2 to 3 dimensions. So recall that in 2 dimensions, the inversion matrix looked very much like the E matrix, except that we had minus 1s instead of 1s, and then the other entries were 0, the other entries that weren't on the diagonal. Again, we extend this to 3 dimensions in exactly the same way as we did for E. We continued down the diagonal, we add a minus 1, and we fill in the other positions with 0s. So this is the 3x3 version of the inversion matrix. Again, we can demonstrate that it acts on a point X, Y, Z. Here, the first row is now minus 1, 0, 0. So we're left with minus 1 times X plus 0 times Y plus 0 times Z, which gives us minus X. Similarly, for the second row is 0, minus 1, 0. So 0 times X plus minus 1 times Y plus 0 times Z gives us minus Y. Last but not least, the third row is 0, 0, minus 1, 0 times X plus 0 times Y plus minus 1 times Z gives us minus Z. So this transforms the point X, Y, Z into the point minus X, minus Y, minus Z. Can we extend the rotation matrices into 3 dimensions? Yes. So let's see how we do that. So first we'll write just a generic Cn matrix and see what that looks like. Recall that this was somewhat complicated in 2 dimensions in that the first entry was cosine of the angle. Here we have minus the sine of the angle, sine of theta, cosine of theta. So we have 4 entries in 2 dimensions. Now, one of the tricks that we use to make writing the matrices as easy as possible is that in most cases we are going to do rotations in the xy plane. In that case, the axis of rotation will be the z-axis, and that makes writing the CN matrix relatively straightforward in 3 dimensions. We continue down along the diagonal, we just merely add a number 1. The other entries will be zeros. So this gives us the rotation matrix in 3 dimensions for a proper rotation. Now, this is using the convention that the rotation is counterclockwise. Suppose we were to do it clockwise instead of counterclockwise. So we had sometimes seen that we could write that as c to the n to the minus 1, and the reasons for that will become clear later on why we use that particular notation. But how could I immediately write down the matrix for this rotation in the clockwise direction, merely knowing the rotation matrix in the counterclockwise direction? Yes, the only change in the matrix is that we change the sign of these 2 terms of the sine term. So here, the minus sign becomes plus. The positive sign here is converted to minus. So this gives us the version if we're doing it in the opposite direction. That's relatively straightforward. So let's put this back to where it was, and I should show you one other thing. So we put it back in the standard form for a counterclockwise rotation. We might also ask, how do I write this matrix for an improper rotation? So one of the nice things about improper rotations, even though it's a complicated operation, it can be difficult to visualize. So recall that we use the symbol S sub n, is that it looks exactly like the matrix for the proper rotation, except that we replace the 1 along the diagonal by minus 1. So we can recognize whether we have a proper or an improper rotation in the xy plane, so long as we merely need to look at the sign of the 1 in this 3rd position here. And that will give us the correct matrix. Next, we want to look at mirror planes, because mirror planes are one of the most important and one of the most common symmetry operations with which we have to deal. So recall that we use sigma to represent a mirror plane. And for example, if we had a mirror in the YZ plane, recall that this would keep anything that had a Y or Z coordinates would stay the same, but it would turn x into minus x. And the way we represent that in 2 dimensions was to have minus 1, 0, 0, 1. And we had noticed that the upper left-hand corner, this particular position, we can think of as referring to the x coordinate. This second position we can think of as referring to the y coordinate. So it becomes straightforward to extend this to 3 dimensions, because if it is a YZ mirror, it's not going to affect the y coordinate either. So this is going to be a 1, and all the other positions will be zeros. So if we're looking at a matrix and we're trying to assign it to a symmetry operation, we would notice that the y and z positions are 1s, minus 1 for x position. So that tells us that we have a YZ mirror. So similarly, we can write down the matrix representations for any of the other mirrors. So long as they're along the axes, they're straightforward to write. So in this case, we notice that x and z, the first and third positions, will be positive 1. The y, which isn't mentioned, that's the coordinate that is transformed, and since it's a mirror, it changes positive y to negative y, and then all the other positions we fill in with zeros. So that gives us the 3-dimensional version for sigma xz. And then the last one, for the sake of completeness, we have sigma xy. And we notice sigma xy, the x and y positions, x and y positions don't change. Therefore, we can interpret that z will change. It's a mirror, so it's going to change z to minus z. So we put a minus 1 in that position, and we put zeros everywhere else, all the off-diagonal positions, and we're left with this particular matrix. So it's good to commit to memory the matrix representations for the most straightforward and commonly used symmetry operations. Now, one other thing which will become important later on, which I can easily demonstrate with these particular matrices. Often in group theory, we do not even really need the exact form of the matrix. Often for each matrix, rather than write out all the 9 numbers that are involved, we often only need to know one number that will tell us most of what we need to know about the matrix. And this particular value is called a trace. And the way I can compute the trace of a matrix is I look at the terms that are along the diagonal, these 3 terms, and I just add them together. So in this case, the trace is -1 plus 1 plus 1, which gives me a value of 1. So I notice that the trace for sigma yz is a 1. For sigma xz, I add the entries along the diagonal, 1 plus -1 plus 1. Here I notice again the trace is equal to 1. So the trace of this matrix is going to be a 1. And last but not least, for sigma xy, I add 1 and 1 and -1. This gives me that the trace again is equal to 1. It's not a coincidence that the trace of any mirror is going to be 1. So that's one thing we recognize right away, is that the trace of a mirror matrix will always be 1 in 3 dimensions. Just for the sake of completeness, let's look at what the trace will be for some of the other matrices that we've discussed. The easiest one we've done so far is the E matrix. And recall that we have 1, 0, 0, 0, 1, 0, 0, 0, 1. So that if I compute the trace, I'm adding up the entries that are along the diagonal. And if I add those together, I get that the trace for the identity is going to be 3. If I take the matrix for the inversion, I recall that the entries are -1, 0, 0, 0, -1, 0, 0, 0, -1. And to compute the trace, we ignore everything that's not on the diagonal. So we only just look at the 0, the -1, the -1, and -1. So in the case of the inversion operation, the trace is going to be equal to a -3. It turns out that there's a process called a similarity transformation, and we can change the form of various matrices so that the entries look different. But one of the important features of a similarity transformation is that the first matrix and then a transform matrix will have the identical trace. So the trace is one of those things that stays even if I change the outer appearances of a matrix. So we say that the trace is invariant. Invariant is merely a fancy way of saying it doesn't change. It is invariant. Invariant is merely a fancy way of saying it doesn't change. Now we would like to write down the specific form of the Cn matrices that we are most likely to encounter. So as a reminder, recall that Cn is equal to and this is where the angle theta is equal to 360 degrees divided by n, or if we're doing it in terms of radians, it's going to be 2 pi divided by n. So recall this is the form of the Cn matrix that we had mentioned earlier. So now we like to do it for certain specific cases. So the first specific case, which is important, is the C2 case. So in this case, for C2, we notice that our angle is going to be 360 degrees divided by 2, so that means theta is going to be 180 degrees. Recall that the sine of 180 degrees is going to be 0, and the cosine of 180 degrees is going to be -1. So that gives us a matrix that looks like this. We have 1, minus 1, 0, 0. We have 0, minus 1, 0. And then we have 0, 0, 1. So recall that in 2 dimensions, the C2 matrix and the I matrix look exactly the same because they share the upper left, virtually a 2 by 2 matrix here, was identical in 2 dimensions. But in 3 dimensions, for the CN, for the C2 matrix, this particular position has a value of 1, whereas in the I matrix it would be a minus 1. So that gives us the form for C2. So now let's look at the form for C3, which is a important and interesting matrix. We had looked at this in 2 dimensions, so it would be simple enough to extend it to 3. Recall that n is 3, so that our theta angle up here is going to be 120 degrees. And we had seen that the cosine of 120 degrees was minus 1/2. The sine of theta was the square root of 3 over 2, which makes minus the sine minus the square root of 3 over 2. 0. And then cosine of theta is also going to be minus 1/2. And then the final position is a 1 because we have a proper rotation. So this is what the C3 matrix looks like in 3 dimensions. And one thing which we can notice about the C3 matrix is that its trace we would get from minus 1/2, minus 1/2, plus 1. So we see that the trace for C3 is going to be 0. So let's kind of write this down to remind us that the trace is 0. So we get that by adding the terms along the diagonal. So that is the C3 matrix. So now let's do C4. C4 is usually the most complex one for which we're interested in the specific details of the matrix. So let's see what we get for C4. Notice that since n is equal to 4, theta is going to be 90 degrees. So recall that the cosine of 90 degrees is 0. The sine of 90 degrees is 1. Minus the sine of 90 degrees will give us a minus 1. 0. So this is what we had in 2 dimensions. And then because we have a proper rotation, and we're rotating in the xy plane, and the rotational axis is the z-axis, this character, and it's a proper rotation, this character has to be a plus 1. So this gives us the exact form for the C4 matrix. For the sake of completeness, we notice that if we add the entries along the diagonal, that the trace of C4 is going to be positive 1. So those gives us the exact forms of the 3 by 3 matrices for C2, C3, and C4. Now, we can write the corresponding versions for S2, S3, and S4 merely by taking the CN matrix and then to turn it into an S matrix. All we have to do is we use the same matrix, but make this final term here change the sign to a minus 1. Now it turns out that in 2 of the special cases, for S1 and S2, we can actually interpret those as another symmetry operation with which we are more familiar. So let's see which symmetry operations those are in those special cases. So for the first special case, let's look at S1. So S1 is going to be exactly like C1 for the x and y position. So recall that for C1, it's just like E, so that's going to be 1, 0, 0, 0, 1, 0. But now, in this Z position, the third row, third column, we need a minus 1. And we'll recognize this matrix. We recognize that it looks exactly the same as the form that we had derived. Notice that it has a trace of positive 1. We have 2 positive ones and a minus one, which tells us that we have a mirror plane, and specifically we have the XY mirror plane. But it's even more than that. We notice that not only the mirror plane, but if we're restricting our high order rotation axis to be the z-axis, so the z-axis would be coming this way, whereas the whiteboard would be the plane of the board, this would be, in many cases, our sigma h. It actually would be horizontal because it would be perpendicular to a high order rotation axis that was in the z-plane. But the thing to recognize is that no matter what our orientation or what other symmetry operations we have in our molecule, S1 will default to being a mirror. Okay. It's going to be a mirror plane. So the other one, which is interesting to look at, and which we can interpret more easily, is S2. So we're looking for the C2 analog, but as an improper rotation. And again, recall C2, which we just looked at a couple minutes ago. The first two entries are -1, and then -1 along the diagonal. And then if it was C2, we'd have a +1 here. To get the improper rotation, the S2, we need a -1 in this position. And we notice now that along the diagonal, the only terms that we have are -1s. So what this tells us, we can recognize immediately in 3 dimensions, this is exactly the same matrix as the inversion operation. So one of the things that we can recognize right away is that S1 is going to be a mirror plane. S2 is inversion. So we can derive those very quickly, and we realize in our future work we will not mention S1 and S2 because we'll think of them more simply as merely being a mirror plane and the inversion operation.